that's the title, and happy birthday to Richard, who's also a joint author of this work. So you find the preprint on archive, as you see. And well, this is ongoing work, so please get in contact with me or Richard for suggestions or criticism. Okay, so there are basically three main points that I want to touch. How can we reduce the computational efforts in ABC when approximating the ABC likelihood by using bootstrapping? A second point is, well, when we introduce bootstrapping, we are introducing some bias in the approximation of the ABC likelihood. We may be able to reduce this bias by using stratified Monte Carlo. And finally, it's interesting to see how using stratified Monte Carlo can help us to use an ABC threshold, which is larger than what we typically would want to use in this type of simulation studies. So what we did was to embed these tools in a pseudo-marginal ABC MCMC sampler, but this is not required. You can use a different sampler. The core of this methodology is about approximating the ABC likelihood, and the way you want to use this approximation is up to you. You can use a different sampler. So here's the usual notation, slide with notation. We are interested in inferring this parameter theta. And we have likelihood, which is unavailable, computational expenses to approximate, and I denote it this way, independence of observed data. So we assume the ability to simulate pseudodata using a stochastic simulator. And of course, we want to use ABC to learn our parameters, introducing some low-dimensional summary statistics of our observed data and simulated data. So the usual setup. And for the very few that are new to this paradigm, well, the key idea in ABC is to give higher weights to the summaries, the simulated summaries that are similar to the observed summaries pertaining to observed data, and therefore accept with a higher probability proposal parameters that make these events likely. Right, so, well, we have the possibility to weight the proximity of the simulated summaries and the observed summaries using a very generic kernel function, which is often a uniform kernel, but more in general, we have this non-negative kernel density measuring the proximity between simulated summaries and observed ones. We have our model simulator here. We have the prior of our parameters. So we define the augmented joint posterior of parameters and simulated summaries in this way, up to a proportionality constant, of course, which don't matter. Throughout, and in the paper, we used a Gaussian kernel to weight the proximity of simulated summaries and observed ones. Other kernels are possible, of course. For reasons that I'm not going to touch in this talk, but they're detailed in the paper, we should not use, in this case, a flat kernel, so not a uniform kernel. Or stratified Monte Carlo becomes vanilla Monte Carlo. But I'm not going to touch on this point during the talk. And what we're interested in is actually the marginal of the parameters, not the joint posterior of parameters and summaries. So we integrate out the simulated summaries, and therefore this is the marginal posterior of our parameters. And this is since we have a prior here, this must be the ABC likelihood. And this is the object that I want to approximate, the main task of this talk. So how can we approximate it? Well, we can approximate it unbiasedly using, for example, Monte Carlo. We can simulate data from our simulator and then take the corresponding summaries so that we can obtain a series of IID simulated summaries, plug them into our kernel, and average over these M simulations. And this is an unbiased approximation of our ABC likelihood. Now, we can plug this approximated ABC likelihood into, for example, a metropolis testing step. So we propose a parameter theta star from a kernel, and we accept it or reject it, well, depending on this probability. Okay, so this is a standard metropolis testing step where we took the approximated ABC likelihood that we obtain using our Monte Carlo approximation. We're going to touch on this point in later slides. And of course, if the model simulator is expensive, and this is basically what we are assuming in this work, having a large number of simulations is really unfeasible. So what it's typically done is that one simulation is produced from the model for each proposed parameter. So m equal to 1. Okay, so this is the scenario. We have a non-negative unbiased estimator here, and it can be of interest to know that this is an instance of the pseudo-marginal approach introduced by Andrew and Roberts in 2009, which means that it doesn't really matter how large M is. Theoretically, the ABC MCMC construct in this way will sample exactly from this ABC posterior. Okay, this is a curiosity. It's not going to be fundamental in the rest of the talk, but again, typically small m is used. Let's say that typically m equal to 1 is chosen if the simulator is expensive. But even though this is a special case of an instance of the pseudo-marginal MCMC, where the value of m theoretically doesn't matter. In practice, it does matter, because if m is low, this approximated likelihood will be very variable. They will have high variance, and it will influence the mixing of the chain. So the larger the variance, the more likely is to overestimate the ABC likelihood, and therefore this can cause sticky chains in our sampler. Right, so the dilemma, which has been already studied previously, is okay, if we choose a small m, well, this will decrease the runtime and we'll have a faster simulation, but well, we will overestimate the likelihood and possibly have high rejection rates, clearly. So is it worth to have a large m, let's say, to reduce the variance of the likelihood, but having a high computational cost? So there has been a study which focuses on using a uniform kernel that says that basically no, it's not really worth to invest computational effort in making m large, and basically keeping m equal to 1 is basically fine. Essentially, the motivation is, let's just run a very long chain, so to compensate for the high autocorrelation. It doesn't seem to be worth to increase m, because m equal to 1 is so much faster. We can just run longer chains. Can we actually do something about this? Can we devise a strategy that allow us to generate many artificial data sets at low cost, and therefore keep the variance of the likelihood smaller than usual? So there is an obvious way to do this, and we're going to consider the pros and the cons of this approach, which has been used by Richard Everett in a paper where a bootstrapping approach has been used within a synthetic likelihood algorithm. So it worked like this. So for any proposed parameter, I'll say that we simulate one data set from the simulator. We call it X star. And from X star, we sample with replacement, and therefore we obtain a bootstrap data set. Each data set that we form in this way will have the same dimension as the original data set, and repeat this bootstrapping or resampling R times. So we obtain artificially R data sets from the one original data set that we simulated from our simulator. How do we do this bootstrapping? If it makes sense, it's up to us to find an appropriate bootstrapping for the case study that we're analyzing. But let's say that we compute the summaries on each fake bootstrap data set, and we denote them in this way, well, then we can approximate the ABC likelihood using the resampled, cheaply produced bootstrap datasets by averaging over them and plug this into the sampler that we want to use. Now, it worked well for the synthetic likelihood approach in this paper. If we do the same within ABC, it's not quite the same. So this approach, it is cheap, it is fast to run. So it's useful when the simulator is computation intensive. And it does reduce the variance of the ABC likelihood compared to when you use m equal to 1 and you don't do resampling. But of course, it's not better than simulate for real m independent dataset from your simulator. Well, this is pretty obvious. Now let's illustrate this concept on a super trivial case study, but it's going to be useful anyway. So we generate 1,000 observations from a Gaussian with known variance and mean theta equal to 0. We want to infer theta. And well, we set a Gaussian prior, so we have a posterior known in closed form. We also have sufficient statistics. So this is the ideal case study. And so what we see on the left is that we have the exact posterior in red, and we have the pseudo-marginal ABC posterior in blue. When at each iteration I simulate M500 independent datasets. And instead, on this other side, we have that at each iteration I only simulate one dataset from the simulator, and I resample 500 times from this one simulated dataset. What we obtain in blue is something that, as you can see, produces a posterior which is much more dispersed. Well, this is not really unexpected somehow. We are introducing some bias due to the resampling step. And let's look at what happens to the ABC likelihood. So what we have is the log likelihood of the summary statistic, which is, we can compute in closed form, of course, this ABC likelihood for this summary statistic. And let's see what happens if I use the pseudo-marginal MCMC with 500 independent simulated datasets. So here I have theta, my mean that varies between minus 0.1 and 0.1. And at each theta, I produce 500 simulated dataset, I compute the likelihood, and I repeat this for 500 times independently so that I compute the mean of these simulated likelihoods and their quantiles. So you cannot see this right now, but I will show you in the next slide. The approximation for central values of theta is pretty good. Again, you will see in the next slide. But on the extreme values of theta, the variance of the likelihood is very large. So you notice there is a factor 10 to the power of 5. And I use a very small delta, okay? So let's see what happens if so now I zoom into this central area of the plot. So this new figure is a zoom in the central area of the plot. And here we have the log likelihood for the exact summary, for the summary statistics that I've observed in black. And we have the mean of the simulated one from the pseudo-marginal MCMC with 500 simulated datasets. There is some bias. This bias can be reduced if I increase M, clearly. Okay, so that's what I wanted to show. But let's see if instead, at each iteration, I only produce one simulated dataset and I resample 500 times. So what you see here is the tails in red of the previous figure, which was of the order 10 to the power of 5. And in blue, here we see the approximated likelihood from the resampling approach when we use M equal to 1 and R is equal to 500. So here we have a 10 to the power of 6 order of magnitude on the tails, which shows why we had such a horrible approximation in the posterior. There is also some bias that you cannot see, but again, the likelihood is also, it's more biased than the previous one. Okay, so we have so much bias. Can we do something about this? So now I start introducing the concept of stratified Monte Carlo, and it's a variance reduction technique. And I'm now going to show some slides in a complete generality, so without ABC. So what I would like to approximate is this integral. It's an integral with respect to a function f and the density p of x over some space d, which I left unspecified. Okay, p is a probability mass function or a probability density function. So, well, this is the integration space, and I want to partition it across j strata that are disjoint because it's a partition that we want to form. Okay, so suppose that we want to integrate a bivariate, that we have a bivariate target, Gaussian target, and suppose that we stratify the integration space across 7 strata. So we have 6 rings, one smaller, one larger than the others, and 7 strata. So from each stratum, in each stratum you have 3 points, exactly 3 points. This is not clearly what we will want to do to approximate that integral. We would like to have more samples in the more internal strata where we have higher mass. So what we should do is, what the statistician should do is, how many Monte Carlo draw to sample from each stratum? This is something that we should decide. Let's see if we can do this actually. And we should decide basically on the number and tilde of samples from each stratum. And also we should know the probability that is enclosed within each stratum. And we call this omega j. So 1 omega for each stratum. And this ideally should also be known. Clearly, this will not be the case in our scenario. But if we have both these sets of numbers, we can approximate unbiasedly the integral using this weighted average. So we should be able to sample from this conditional density, conditional on the fact that we are in a certain stratum. So we want to sample nj times from this stratum, and we plug these simulated values, so we sum across each stratum, and we weight these samples, and we obtain the stratified Monte Carlo sample of this integral. This is unbiased, it's easy to prove. Okay, well, it can be, in the ideal case, there are some known strategies to reduce the variance of this approximation, but we're not going to look at this because this is the very ideal case where these omega are known and where we are in control of the ability to sample from each stratum. But we cannot actually do that. So we cannot really decide how many times to sample from within each stratum, because in the first place, we don't know how to sample inside each stratum. And we don't know these omega probabilities. So what we can do is to use what Art Owen has called post-stratification. You can find this very nice monography online. It's freely accessible. So this post-stratification approach means that we generate from the unconditional simulator, so not conditionally on a specific stratum, we just simulate from our model simulator, X star, and then we count how many of this simulation end in each stratum. So the number of points in each stratum is now random, while previously was decided by the statistician. So we can only know this nj after the simulation is performed. And well, we still don't know anything about this. So we can approximate this omega actually quite easily. And now we are going to show how to do this within ABC. So we assume that we have a Gaussian kernel, and this is the integral that we want to approximate. And we have this integration, the space that we want to partition into strata. So a very trivial way to do this is to say, okay, we have our ABC threshold. We could define the strata in the following way, like the set of simulated summaries that fall far from the observed ones within a certain radius. This is the most internal stratum. The second stratum will be the summaries that fall within a radius delta and excluding the most inner stratum. And the third and last stratum could be everything that is left. So for example, if we use an Euclidean distance, this could be a trivial way to approach this problem. And yeah, for each theta, we can resample 500 times from the one simulated data set from the model. Okay, and then we can count how many summaries fall inside each stratum. This gives us the numbers N1, N2, and 3 that we'll need in our approximation. Okay, so this will be graphically what happens at a certain theta. We simulate these blue points, and then we count how many fall inside each circle, inside this disk, each disk. Okay, but we still need to estimate this omega, and this can be done via a second MC Monte Carlo simulation. Basically, the omegas are defined by this integral. And we can do at the certain theta, we can simulate one more time from the model, resample from this data set that we simulated to produce our data set. But by bootstrapping, we compute again the corresponding summaries and these distances, and then we just say, okay, let's compute the frequencies, the proportions, where these distances are within a radius delta divided by 2, or between delta divided by 2 and delta, and by difference, we obtain the last proportion, omega 3. So according to this approach, which at each proposed theta, we should simulate twice from the model. Once to find the frequencies N1, N2, and 3, and once to obtain these omegas. So we have two simulations from the model for each iteration. And then we can have this approximation, which is biased, unfortunately, because these are estimated. Okay, so again, this is what I just said. We need to simulate twice at each theta if we want to follow this approach. And what happens actually if sum of these frequencies is 0? So what happens if one stratum is neglected? One stratum doesn't have any simulated sum. That would be a problem because nj is at the denominator. So what we do is we introduce this indicator and we force this estimator to be exactly 0 as soon as one stratum is neglected. Okay. Now we will see that this is both a curse because this will increase the rejection rate, but it's also a blessing because this is the one reason why we can reduce a lot the variance of our ABC likelihood and will allow us to keep the delta not necessarily too small. We will see this and why this happens. So let's say that we plug this stratified estimator from this, using this formula, into our Metropolis Hastings, yeah? And then we iterate Metropolis Hastings as usual. Or you plug it into your favorite sampler, like SMC, for example. So what happens if we use this approach on the previous toy model? This was, again, pseudo-marginal MCMC using 500 simulated data sets and a very small delta. This was the case where we simulate only once from the model and 500 resampled data sets at the same small delta. And this is when we use one simulated data set, resample 500 times, and we introduce some stratification. This is what we obtain in blue. So we get results that are as good as the standard pseudo-marginal with 500 independent data sets. But notice that here we had to use a large delta, or otherwise we have lots of rejections. We used a delta which is 10 times larger than the delta that I used here or here. But I got good inference. So if the model is simple enough, well, there's not really a problem. We can run many, many iterations if we have the computational power to do so. That's always the case with ABC. But this means that, well, even if the ABC likelihood is better approximated, so it's highly variable, and the chain mixing could be poor, well, we just need to run many MCMC iterations. And this will compensate for having a bad mixing. What if the computational power is limited? What if we cannot really run all the many iterations we will want to? Well, if the model is complex, we can use a larger delta and employ stratification to compensate for using a large delta. I'm going to detail a bit more on this. I think I skipped some slide. No. Okay, so what happens if you have a very small delta, which is what we usually want to do in ABC to obtain accurate inference? Well, if delta is very small, assume that here delta is very small, well, the ABC likelihood is, of course, very concentrated around your observed summaries, which means that most summaries will fall far away from the observed ones, and therefore will fall far away in the tails, which means that you will obtain a poor ABC likelihood approximation with high variance. And typically also, you don't even have all these many dots. You are not in the position to simulate many times from your simulator. Anyway, maybe you simulate only once or twice, and therefore you obtain a poor ABC likelihood approximation. And if you have a few iterations that you can perform, that's going to be a problem. It will cause high variance in your ABC likelihood, and therefore sticky chains. But if you have a larger delta, we can have more sample in higher probability regions. And using stratification, we can obtain a better approximated likelihood, but a better approximated but wider ABC likelihood. So this is a bit a trade-off. Shall I use a small delta, but that gives me a very variable ABC likelihood, or can I instead use stratification and resampling to accurately approximate a wider ABC likelihood? How can this work if I use a wider and therefore more imprecise ABC likelihood? Well, the trick is to only accept the theta when all the strata are represented. You need at least one sample in each stratum, okay? And this can be done if you use resampling, because you can cheaply resample many, many times, so to have many samples and hopefully one falling in each stratum. It's important that you have a stratum, that you have a sample in the most inner stratum. Now, this will have consequences. Let's see if it worked using this approach in the approximation of the ABC likelihood. So we have the ABC likelihood approximated and for different values of theta. M equal to 1, 500 bootstrap datasets, and stratification. So this is what happens. And we don't have an order of magnitude of 10 to the power of 5 or 10 to the power of 6 in the tails anymore. This is what happened when I use standard pseudo-marginal ABC with 500 independent datasets. Remember the 10 to the power of 5 in the tails. And even larger when we use resampling without stratification. So this is really crucial. This is the crucial part that we need to consider. And in order not to have a zero stratum, we need to use a larger delta. Yeah, a larger delta that give me a wider likelihood, but that is better approximated using resampling, using many resamples, so to have one sample at least in each stratum. So can we actually even reduce further the variance from this approach? Yes, we can do that. We can do something even more. At each proposed parameter, this is what we did until now. We simulated once from the model, we resample, and we obtain the strata frequencies. We simulate once more, we resample, and we estimate these probabilities. So we earn one ABC likelihood approximated with stratification. But we can obtain at zero cost a second ABC likelihood because we can swap the roles of the simulated data set that we obtain in these two steps. What if we now reuse the simulated data set that we obtain with resampling here to estimate omega j and use the ones that we simulated here to compute the nj? So we swap the roles of these two sets. So now we can obtain at zero cost, a second likelihood, ABC likelihood, at the same iteration, and we can average the two. This is from the original approach, and this is the one from swapping the roles of the simulated summaries, and we average them, and we halve the variance of the ABC likelihood. So what we obtain here is that if we don't do this averaging, this is the variance of the ABC likelihood with stratification. If we do this averaging these two different likelihoods, this is the variance of the averaged likelihood by swapping these samples. So if I have 50% reduction. Okay, so what's the issue? We cannot create as many strata as we want, because if we introduce more and more strata, it's more likely that you have neglected strata. So we had to keep this the number of strata small. We chose to consider 3 strata, but we don't really have a theory for choosing the number of strata and how wide this strata should be. So this is further research. And again, keeping a larger delta, it's okay if you use this approach here. So also, doing this resampling causes some overhead. The simple fact of resampling data that we have simulated, well, causes some overhead. Is it worth it? Let's see. So we would like to now do a more complicated example. So time series. And let's assume that we have a time series and we want to use a specific type of bootstrap. It's the block bootstrap that is introduced in this paper, where we don't resample observations, but we resample indices. We resample blocks of observations. So this is what we do. We have, let's say, all our observations. We split them in different blocks of observations, and we resample the blocks, not the individual observations. So we would like to do this in a way that the blocks are sufficiently large so that we can keep the properties, the short-range properties of our time series. And the fact that, and we would like also to have large enough blocks so that when we resample the blocks, we keep the same statistical properties of the real data. So it can only be applied in certain situations. And we do this at each proposed theta. So we resample blocks of indices. And what is a presentation without a Lotka-Volterra example? There has to be a Lotka-Volterra example. So for those of you that are unfamiliar with this example, it's about considering 2 interacting species that you can imagine as the predators and prey. There are 3 types of interactions. A prey may be born, the predator and prey interact, and the prey dies, or the predator may die by natural causes. And this can be, the likelihood is intractable, but it can be simulated exactly using the Gillespie algorithm. Yes, Xian, there has to be a Lotka-Volterra example. So this is a simulated data set. We have 32 observations for each population. So you see that, well, there is some regularity. So we can assume that the first 8 observations could constitute one block. The next block could be the next 8 observations, and so on. So we could have blocks of 8 observations. So overall, 4 blocks for 32 observations. We have 3 parameters to estimate. We put this on informative priors on the parameters. We run a pseudo-margin ABC with 2 independent datasets simulated at each iteration, right? It's a bit computer expensive, so we use m equal to 2, and no stratification. Then we do ABC MCMC with 2 independent datasets at each iteration and 500 resampled datasets. So this is the stratified approach. We use 3 strata, for example, of this type. And then we have an expensive ABC sequential Monte Carlo with 1,000 particles. It requires 12 hours of computation, but we consider this as our gold standard. And this is a very nice ABC SMC. It's a generalization of the paper by Del Moral, Jasra, and Doucet. You can find them into the ABC handbook, but also on Archive. It's a standalone chapter that you find in Archive. And it's a generalization in the sense that you can use a generic kernel, not just the uniform kernel from Del Moral. It's also nice because it has an adaptive way to choose the thresholds. So they don't have to be chosen in advance. So what the ABC SMC gives us is that after 12 hours, it finds an optimal delta. And by optimal, following their approach means that we have a 1% acceptance rate. So it decreases for 12 hours, and then it finds this delta automatically. And we consider the inference that we obtain as our gold standard inference from ABC SMC. So we have these 3 different results. ABC SMC with this delta, pseudo-marginal ABC with 500 simulated datasets at each iteration. We have to run it with a slightly larger delta, or this ABC MCMC doesn't really doesn't produce any acceptance, so it's slightly larger. And then our stratified ABC with a delta which is 6 times larger than this one. So what we obtain here is that, okay, the pseudo-marginal version, well, overestimates the quantiles at 2% and 97.5%. This is because it mixes poorly. With a small delta and 10,000 iterations, we have a very few acceptances. We have a variable, very variable likelihood, and therefore it mixes poorly and it explores the tails poorly. We cannot run it for as much as we want because it's expensive. Instead, if we increase the delta and we use stratification, we obtain an exploration of the tails, which is just as good as gold standard SMC. But we obtain a much larger acceptance rate, even though the delta is much larger than before. We have a better ESS, the effective sample size. And even though it's slightly more expensive to run than pseudo-marginal ABC, well, the ESS per minute is much larger for stratified ABC. So overall, it's 4 times more efficient than the pseudo-marginal version. So I'm going to conclude quickly. Well, not quite, but almost. So here I just show you what happens with 10,000 MCMC iterations without stratification. Without stratification, this is what we obtain. This is a sticky chain with m equal to 2 and a small delta. This is what you typically obtain. And this is what we obtain with our approach. Even though delta is larger, the inference is preserved. We have a better mixing. And that's because we reduce the variance of the ABC likelihood. So we have a better variance, so better, in the end, a better mixing because we have a less sticky chain thanks to a smaller variance in the ABC likelihood. So the conclusions is that if you use stratified Monte Carlo and know how to build it, this is quite effective in reducing this bias that is brought by the bootstrapping approach. We can obtain a precise ABC even though we use a larger delta by reducing the variance of the ABC likelihood. The downside is that we might have neglected strata. So to reduce this chance, we have to resample possibly many times. In this case, 500 times it was fine. And we need some way to approach high posterior mass. And for example, we can start the simulation using resampling without stratification. This will allow us to reach a high posterior density without introducing stratification. And only when we reach that area, we can employ stratification to refine our inference. There is an example in the paper that does that. And of course, we need to have data for which bootstrapping makes sense. We need to have a resampling strategy that makes sense for our model and our data. And finally, we need more research to know how many strata to introduce, how to construct them, how large should they be. This is not something we address. So we will really welcome your comments. You can contact me or Richard. And I would like to let you know that I'm advertising a PhD position with deadline on 29th of May of simulation-based Bayesian inference and interactions with deep learning. This is the link. Thanks so much for listening.
Thank you very much, Umberto, for the very interesting talk. Any questions? Please use the raise the hand icon.
Okay, I'm seeing that we're receiving plenty of questions, but should I look at who raised the hand or what? I don't see any raised hand.
Yes, so Christian has a question. Please go ahead.
Okay. Yeah, thank you, Umberto. I find quite interesting this aspect that you can switch to a different delta, because originally you're trying to approximate a quantity that is the ABC likelihood, not the exact likelihood, and so originally it should depend on the delta rather than allowing for a switch in delta. So could you extrapolate a little bit on that?
I'm not sure I heard the last question. So yes, it depends on delta because we are targeting a likelihood which is attached to the specific delta that we are considering. So yes, we don't know really which likelihood we're approximating. We are approximating, well, we know which one, but it's again, it's depending on the delta. So we cannot say that we are approximating the likelihood of the non-ABC likelihood. We are approximating a likelihood which could be possibly imprecise in the sense that it's wide, okay? And what we want to do is only to reduce the variance of this approximation. It just seemed that it works better to approximate an ABC likelihood which is wide using many samples and having a low variance rather than approximating a very narrow ABC likelihood for which we have very few samples in the important part of the integrand, and therefore that would be very variable. But again, yes, it's a strange likelihood that we are approximating. It really depends on the specific delta. I'm not sure if this answers your question, honestly.
Yes, it does. Thank you very much.
Any further questions? So while we are waiting, perhaps I would have a question. So Michael is here speaking. As you mentioned, the approach depends a bit on the ability to do reasonable stratified sampling. So if you say in the time series, if you get the block size a bit wrong, or just if you use different block sizes, how sensitive are the results to different choices of the block size?
I could tell you if I did try, but I didn't. I think that for an example like the one that I've shown, it's perhaps not too sensitive to the size of the block because we have such a regular behavior in the, yes, we have this very regular behavior, so perhaps it doesn't matter that much. But if you consider a very non-stationary time series, I can imagine this could cause problems. So again, it really depends on whether bootstrapping makes sense for your data. I cannot say that it always makes sense. Probably it doesn't make sense all the time. You need to have blocks that somehow contain enough information about your parameters within the range that you consider for the blocks. It's fairly intuitive to imagine that we cannot afford having blocks that are too narrow and therefore might not have enough information for each parameter that you want to infer.
Okay, thanks.
Yeah, okay, now I finally can scroll through the many chats, but I
think a lot of
doesn't seem
clapping
like
in the chat, which is good.
but the clappings are only for Richard and Massimiliano. It's their birthday, I suppose. Yeah.
Any further questions? Okay, if not, we clap again, and this time we make sure it's for you, Umberto. Thanks again for your very interesting talk. Many thanks.
Thank you very much. Have a good rest of the day.